One? Yeah? Okay. Hello. Thank you very much for coming. My name is Warski. I come from Poland. And I would like to talk today about how to construct three things. So if you have been on some previous talks, you may have seen some more abstract constructions of three monads and three monads and so on. So in my talk, I will try to take a more constructivist view of things. And we will, in fact, not talk about category theory at all. We will start with algebra and take it from there. Okay, so what's the overall plan for the next 50 minutes or so? So first, there will be a short motivation. Why should we be bothered with three monads at all? Then I will introduce 5 basic concepts, which will lead us to the definition of a free thing, of a free object, free algebra, and a free monad as a more special case. And finally, we will look at how free monads are defined in Haskell and Scala. So when you're listening to the talk, keep in mind that it's all quite simple. So there is some math, but I think the math isn't very scary. And overall, the concept is quite simple. So don't look for a deeper meaning where there isn't one. And if you have any questions throughout the talk, please ask. Okay, so why should we bother with three in the first place? So I'm not going to do like a tutorial on what a free monad is and how to use it in Haskell or Scala. There's plenty of material on the web on that, and there are some very good blogs, talks, and so on. So just a short motivation why, if you haven't yet used free monads, or if you're not familiar, why should you look at them? So the goal when using free monads in your code is to separate the definition, the description of the program from its interpretation. So using a free monad, we can create a high-level DSL with which we can describe a solution to our business problem, and then provide many interpretations for that DSL. For example, one interpreter can be for tests, like using, for example, an in-memory database. Another interpreter can be a production interpreter using a real database. With the free monad, programs are represented as values, which can be composed together to produce bigger programs, bigger values. We can manipulate those values as any other value in our code. And that value is the description of the program, and then we can apply an interpreter to that value to get the result to actually run the computation. Okay, so that's like a very short motivation. So, but in fact, you don't really need to know anything about free monads to hopefully understand what we'll be talking about. That's just like a teaser. If you haven't used them, take a look to find out more. Okay, so let's start with these 5 concepts that I've been talking about. So the first one is algebra. Okay, if you go to Wikipedia and if we search for algebra, we can read that algebra is the study of mathematical symbols and the rules for manipulating these symbols. So algebra is kind of like syntax with which we can express our thoughts, our problems, together with some rules on how we can manipulate this syntax. So we see quite a lot of examples throughout our lives of various algebras. Okay, so a very simple example is like the linear equation, right? There are some symbols involved, like probably suspect that x is a variable, a and b are constants, and so on, right? So we have some other symbols like plus and equals here. And there are some rules how we can manipulate them. There's a lot of other algebras that we encounter in everyday life, like E equals mc squared, right? It's like an everyday thing. We can invent our own symbols, our own rules for manipulating them, or we can even go as far as doing this or this. These are also algebras, right? We have some symbols, we have some rules on how we can manipulate these symbols, right? Either in Scala or in Haskell. So these are all algebras. Each one is distinct, each one has its own set of symbols and its own set of rules. So what we will be looking at is universal algebra. So universal algebra takes this a level higher and it generalizes the concept of an algebra, right? So before we had some very specific symbols that we were looking at. So here we will be looking at algebras like in general. We will be looking at algebras with any kind of syntax. So universal algebra is a study of general algebraic structures rather than specific models, as we have seen before. Okay, so to talk about any algebra in general, we need a way to formalize the syntax. The syntax will consist of two things. So I like static typing. So we will have multi-typed algebras. So an algebraic signature, and that will be our syntax, consists of two things. First is the set of type names. This will be set S, and another will be a family of sets of operation names. Okay. Now each operation has a potentially empty series of types of its arguments and a single result type. Okay, so the S star is like a sequence of type names, right? It can be empty, it can be like 2, 3, and so on. And the second the second element of the product is the resulting type of the operation. Okay.
Where is the family?
It's a family because each operation consists to a specific has a specific arity, right? Okay. So there will be a set of operations with two arguments of a given type and a given result type, right? And there will be another family of sets with 3 arguments and so on. So it's a family of sets.
What about the star for S?
The star is like a sequence. So it can be 0, 1s, 2s's, and so on. Okay, you will see an example in a second, so maybe it will be more clear. Okay, so the algebraic signature, we will denote it as a sigma, and that defines the syntax of our algebra. And that's pure syntax, no interpretation yet. So as an example, we can have 2 types. So S at the top, that's the set of type names. We will call our types int and string. So you kind of suspect what this might be, right? But these are just names, okay? These have no meaning at all. And then we have a family of sets of operation names. So here for each combination, we only have at most 1 operation, but we can have potentially many operations, right? So for example, we have in the second row, we have a single operation which takes no arguments and has type int. Okay, so that's a constant 0. We have the successor operation which takes 1 int and returns another int. Okay, is that more clear now? Yeah. Okay. And similarly, like we have an operation which takes an int and returns a string, and its name is toString. We have a family of operations which takes 2 strings, returns a string, and its name is double plus. So the important thing to remember is that these are just names, okay? Only syntax. And using this syntax, we can now produce kind of expressions, programs, however you want to call it, right? So for example, here we conversed the successor of 0 added to the successor of 0 to a string. So that's like a well-typed expression using this syntax. Okay, I guess it's quite familiar if you've been doing programming. So another example which we'll be using later is a much simpler signature. So that's like another signature with a different set of symbols, right? Here we have 1 constant 1, and we have 1 binary operation star, and we have only one type name. So we can define various signatures in that manner. Okay, so that's the signature. That's the first concept. Let's proceed to the next one. So now in algebra, in the scope of universal algebra. So in algebra, we will say that it's a specific interpretation of a signature. Okay? So the signature defines the syntax, the operation names, and now we have a specific interpretation. We can have many interpretations for a given signature, right? So an interpretation consists of an interpretation of each type that will be a set of values that the type can that values of this type can have, and for each operation it will be a function between the appropriate sets. So for example, if we take the signature as we have defined it in our first example, right? Two types, some operations on these types. Now we can define an algebra. We will say that an algebra with signature sigma will be a sigma algebra. Okay? So we can define a sigma algebra. We will call it A. That's like one of many possible algebras for that signature. So we can say that the interpretation of type int will be natural numbers, and the interpretation of type string will be all strings from Latin letters. Okay? So for each type we assign an interpretation, a set of values. And now we have to provide also an interpretation for the operations. Okay? So we say that successor is a function which, if you remember the signature, it's a function which takes an int and returns an int. So it's a function which adds 1 to its argument, right? So it's a function from ints to ints. Ints interpreted in our algebra as natural numbers, right? So that's a word from the operation. And in a similar manner, we can define other operations. Okay? We can also define other algebras, right? We can define a sigma algebra B, where the interpretation of ints, for example, are whole numbers, right? It will be a different algebra for the same signature. Okay. So we now have the syntax, and we have an interpretation of the syntax, which are algebras. As a side note, if you've seen maybe in Haskell and Scala a concept of F algebras, so that's related. So an F algebra is a generalization of a single-typed algebras as described here. So these are the same algebras, only the F algebras with a single-type parameter correspond to the single-typed algebras as I described them here, right? If you wanted to have multiple types, you would need multiple type parameters with an F. But that's just a side note so that you can make the connection between the various concepts. Okay, so these are two concepts of signatures and algebras, and now the third concept, that will be almost the half. So now we will build a special algebra that we can always build, and we will call it the term algebra. Okay, so the term algebra consists of pure syntax, no interpretation at all. It will consist of pure syntax. Okay, so the term algebra is rather boring. There's no interpretation, as I said, and we define it. I will define it by example. So again, we take the signature as we have seen it before, and now we define the term algebra. The term algebra for a signature sigma is usually written as T with the sigma index, as term algebra for the specific signature, right? Because it's always in the context of a specific signature, right? So the signature is kind of fixed but arbitrary. Okay, so now we have to build an algebra, we have to provide an interpretation for each of the types. Okay, so here the interpretation of the int type in the term algebra will be all expressions of type int that we can build with our syntax. Okay, so that's obviously 0, the constant, successor of 0, 0 plus 0, and so on. Okay, so these are like all valid programs, all valid expressions that we can build with the syntax. And similarly for string, right? You can think of it as like abstract syntax trees and so on. It's not visible here, but like the parentheses matter here, right? Because these are like, so 0 plus 0 plus 0. So that will be 0 plus 0 plus 0. Is a distinct expression from that, right? Plus 0. These are two different trees. Okay. So now we have an interpretation for the types. We also need to provide an interpretation for the operations, right? And this will be rather simple. So for example, an interpretation of the successor operation in the T sigma algebra, given any term, any expression here, will be like a new expression built out of the successor name and the term, right? So these are like different. These two live in different worlds, let's say, right? So that's an interpretation. That's an interpretation of an operation in the algebra, and that's just a name that's like applied to the term, right? So that's kind of a string, an abstract syntax tree, and that's like a function, right? So for example, the successor as interpreted in the T sigma algebra of this expression will be an expression like that, right? So that's, I guess, the most boring interpretation that you can think of, but that's how the term algebra is defined. Another way to think about it is that the term algebra is defined inductively. Okay, so as the induction base, we take all constants in the, because we have to start building the expressions somehow, right? So we take all constants, so we have a single constant here, right? And then, as the induction step, we apply any functions that we can to the previously to the previous set, to the previous step. So the induction base is just a single constant 0, right? In the next step, we apply it. We can build expressions like these, right? We can add to zeros. We can take a successor, and so on and so on. So this grows larger and larger and larger. In a similar way, we can build a term algebra for the other signature that we were looking at, right? With a single type and two operations. And as I've been saying, like the parentheses matter, right? So that's a different term than this, okay? Because it's like a different tree. Okay, so that's the third concept. To go. So,
can I ask
yeah, sure.
how does a term algebra relate to other algebras? Is it like
We will be talking about that in step 5,5. Okay, so now a homomorphism. A homomorphism is a function between algebras, okay? So now let's say we have a fixed signature, we have fixed syntax, and in our world we only consider all algebras for that, which are an interpretation for that signature, okay? So in this world of algebras for which are an interpretation for a given signature, we can define functions between algebras, between these interpretations. But these are not arbitrary functions. These functions have to be such that the operations are preserved, okay? So again, the same syntax, the same signature as before. And now we say that a function from algebra A to B is a homomorphism, or that f A to B is a homomorphism between the algebras, if we have a pair of functions. So we need to have a function between an interpretation for each of the types. Okay, so that will be two functions in our case, because we have two types, such that the operations are preserved. So they are like well behaved. What does it mean that operations are preserved? Well, for example, if we take any x which is in the domain of ints from the algebra A, and we take the successor of x and we translate it with our homomorphism, that's the same as taking the successor as interpreted in B of the translated x. Okay, so we can like take the operations outside of the parentheses, right? So this operation moves outside here, right? So that's what defines the homomorphism. So that it's like a family of functions between the types, such that the operations are preserved, right? So that it doesn't matter if we first apply the successor and then translate, or if we first translate and then apply the successor. Okay, so that's the operation preserving property that the homomorphism must have. Okay, so that's 4. And that's now we'll answer the question about the relation between the term algebra in a way. So now we will say, we'll define a property of algebras. Again, we have a fixed signature sigma. And we will say that an algebra I is initial when, so we take the algebra I and it is initial. Now if we take any other algebra A, there will be exactly one homomorphism from I to A, okay? So, and I is special because if we take any other interpretation of that signature, there's only one way we can define so there must exist a homomorphism from I to A, and there must be exactly one way to do it such that the operations are preserved, okay? And now there's a nice result which says that our term algebra is initial, okay? So why is that? So I will do a proof by example. So we want to see that the term algebra is initial. Okay. So how do we approach that? So again, we take any signature. We take our example signature as before. We take our example. So now we need to take any other sigma algebra, right? So we take the algebra that we have defined before. So that's A is like definitely not the term algebra, right? So it's any other algebra that we.
Can I make you a question?
Yeah.
Why 0 is an operation? Is it related with ints?
Is it related with ints? Well, it's just a name. It's really so it's just a suggestive name, but it can be anything, right? We can interpret it any way we want.
So it's not related with the.
So in our so here we have like defined that. So we have defined a specific interpretation of the signature. That's the algebra A, and in that algebra, ints are interpreted as natural numbers. But in another algebra like C or D, they can be interpreted as real numbers. They can be interpreted as strings even. Why not?
But in this case, there is a link between 0 as an operation and
the
first element of the natural numbers.
Yeah. So Okay. Okay. So we have this algebra A, and now we want to see that the term algebra is initial, and to do that, we must show that there exists a homomorphism from the term algebra to A, and that there's exactly one such homomorphism. Okay. So how do we do that? Well, if we take a look at what does it mean to be a homomorphism, we will see that the translation of the term 0, right, of the constant 0, must be 0 in algebra A, because that's exactly what the definition of the homomorphism says, right? Similarly, the successor in the term algebra of any term translated must be the successor of A of the translated term, right? So you can see the induction here, right? So in the end, what we arrive at is that if we take any term over here, so this homomorphism will kind of evaluate that term in algebra A, right? So this term here is like a program written using the symbols, the syntax from sigma, right? So that's a program, and that's like a specific interpretation of how these symbols really work. So what we do is we take that program and we evaluate it here, right? And that's our homomorphism, right? And it is a homomorphism just because that's exactly these are exactly the conditions that these functions must meet for it to be considered a homomorphism. So is it clear more or less?
Yeah, but how do you show it's unique?
How do I show it's unique? Okay, so again, using the same argument, so if we have any other function, let's say g, right? So g applied to the term 0, right? It must be translated to the interpretation of 0 in A, okay? So g on 0 must be the same as f on the 0, right? Now, if you take any other term, and now by induction, right? G on the successor of any term must be the same as successor of g of t, right?
Is that like a proof by contradiction?
No, by induction. That's the induction base, right? That's the induction base, right? We do a proof by induction on the size of term t. So let's restrict our attention to only this signature, right? So that's like the base case, right? Any homomorphism between T sigma and A must meet this condition, because that's what it means to be a homomorphism. And now, if we take this, So any function must meet this condition as well, because that's the definition of a homomorphism, right? But you can see that this is a smaller term, right? So for any other g, g of t will be equal to f of t because of the induction induction step. So this must be equal as well.
I just don't see what's special about coming from the term algebra, because you could have homomorphisms from like A to B, general algebras that are not unique.
Yeah. Okay. So the what's unique about the term algebra is that the homomorphism always exists, right?
Okay.
So, like in general, if you take any two algebras, there doesn't need to be a function between them.
But there could be two. Also.
Well, there could be two, right? So what's special is that the function always exists, always,
Yeah.
and that is always unique. So that's what's special about it. That's the whole point of the term algebra. Okay. So what the initiality of the term algebra really says is that there's only one way to interpret a term in a target algebra. Okay? And it has like two important properties. So the term algebra contains no junk, so there are no additional elements. It contains only what's really necessary, only what the signature like forces the term algebra to have, right? So the term algebra only contains what's generated from the syntax, from the operations. It doesn't contain any extra elements. And also there's no confusion, so if in any algebra two expressions can have a different value, they will be distinct terms, right? Because in theory they could be interpreted in a different way. So the term algebra provides no interpretation at all, it just provides the syntax which can be then evaluated. So as an example of an algebra which isn't initial, let's take the same A algebra, okay? As we have seen before. Now this algebra definitely isn't initial. So it contains some junk, some extra elements. The strings A and B, right? They are not reachable by any term. So we cannot build an expression from these symbols which will evaluate to A. We just can't, but the algebra can contain them, why not? And it also has, it also contains confusion, so in this specific algebra, 0 plus 1, or the successor of 0, is the same as successor of 0 plus 0. But in general, it doesn't have to, right? This can be, in some other interpretation of the same signature, these can be distinct values. Okay, so we are almost there. We just need one more twist, and we will get to the freeness. So, now we will enrich our terms a bit. So we will add variables to our terms. So if we take a set X, that will be our set of variables. We can define T sigma X as the term algebra of X with X added as constants. So it will be terms with wholes from the set X. Okay? As an example, again, it's the same signature as before. So we take a set X of variables. In fact, it's a family of sets because for each type we need to have distinct variables. So we have 3 variables of type int, I, j, k, and we have 2 string variables, s1 and s2. Okay, so that's like we can take any set of variable names. In fact, not variables. We take any set of variable names and we add them to our signature, right? And now we can build terms with wholes, right? So these are again terms built using the language defined in sigma and with variables from X. Right? So we can build a term like successor of I plus j plus successor k. Right? So these are like, that's the same type of construction, just with the X added as to the signature. In a similar way, we can add variables to the other signature that we've been talking about and build terms using these variables. Okay, so now we arrived to the free algebra. So first there will be a definition, it's a bit dense, but there will be an example later, don't worry. So first we will look at, again we have like a fixed signature sigma, okay? And now we say that an algebra I is free over X. So what is important here is both the I, which is the special free algebra, and the set X, which is the set of variables. So we say that I is free over X now if we take we take any other interpretation, any other algebra A, and we take any function from x to A, and this has to extend uniquely to a homomorphism between these algebras, right? So in the initiality condition, we only require that there always exists a function from I to A, right? Here we have the additional complication that this function needs to extend the function from x to A. Okay. So maybe not very surprisingly, it turns out that for any variable set x, the term algebra with the variables from x is free, according to that definition. Okay? What does this definition really mean? It means that if we take a variable set x, we build terms using our signature, our language, with variables from the set x, and now if we take, if we have an interpretation of the variables, so that's an interpretation of the variables in our target algebra. So if we take an interpretation, this extends uniquely. So there's only one way to extend this function to a homomorphism between the term algebra and A. Okay? So evaluation of the variables determines the value of any term built on top of these variables. So an example is, I guess, needed. So same signature as before. Same variables, right? So we have the signature above there. We have the variables ijk, s1, s2. And now if we want to show that T sigma x is really free, we need to take any other algebra A. So we take the same algebra A as before, which interprets ints as natural numbers, strings as strings. There's the interpretation of the functions. So now we define a function which interprets the variables from x in our target algebra A, right? So in this specific interpretation, we interpret I as 10, we interpret s1 as lambda, s2 as conf, and so on. Okay? So that's this over here. That's evaluation of our variables, right? It can be any evaluation, but that's a specific one. So now we define an extension of that function to the term algebra, right? And that again follows the same principle as before. We can define it by induction. So if we take any term, for example, like here, right? We can evaluate it. We can evaluate that term in our algebra A. And when we encounter an operation, we take the appropriate operation from algebra A. When we encounter a constant, we interpret it as in A. When we encounter a variable, we look at the function over here, right? And again, inductively, we can say that the f sharp will be an evaluation of that term in the environment defined here, right? Yeah.
It's because you weren't able to produce lambda or conf given.
That should be S1, by the way.
The algebra only had two string of integers basically, so your alphabet was like 0, 1.
Yeah, but that's okay. So this that's S1, right? So that's a variable of type string, right? So if we want to interpret S1, we look at our algebra doesn't contain S1, right? Our signature. Yeah. So we have to look at the interpretation over here, right? Yeah. It's yeah. I know. It should be S1. Let's pretend it's S1. Okay. So and that's like that's what how the free works. So in the free algebra, what it does is so the free algebra being the term algebra, right? It's an algebra which doesn't provide any interpretation. Its elements can be interpreted in any way, right? So, and that's where the free comes from, right? The algebra is free from any interpretation. There's no constraints. So that's where the freeness is. And that's why it's called free. It's also free of any additional structure, right? It only contains what's absolutely necessary. Okay? Following the same names as we have seen in the initiality, there's no junk, so the term algebra doesn't contain any extra elements and doesn't confuse any elements if it doesn't have to. So that's how you can create a free thing for any signature. And before we get to free monads, a small sidestep. We'll complicate things a bit. We will add some constraints to the interpretations of our signature. So the interpretations are the algebras, right? So we will add equations. So before we had the signature, but the interpretations were totally unconstrained. They didn't have to meet any conditions. And now we will say that we want our algebras to actually meet some conditions. And these conditions will be expressed as equations. And we'll write these equations using the term algebra, right? Because the terms are a very nice way to represent expressions built out of our syntax. And we will only focus, so before we considered all algebras for a given syntax, now we will only look at algebras satisfying a specific set of equations. Yeah?
Did you define what a sort?
Oh, a sort is a type, sorry. Okay. Sorry. So the math people talk about sorts, but we are more used to types, but it's the same thing. So for example, if we take now our simple signature, right? Single type and two operations. One is a constant, star is a binary operation. We can define a set of equations for that over that signature, right? We can say that for any x, y, z, x times y times z in parentheses has to be equal to x times y in parentheses times z. And that one is a neutral element. So these are the equations saying that this has to be a monoid, right? So we will now only consider interpretations of this signature which are monoids. So we restrict our worldview. So now what's the question, of course, is what's the free object in the world of monoids? That's like a natural question we want to answer, of course. So unfortunately, our term algebra for any set of variables doesn't satisfy the equations, right? Because x times 1 is a different term than x. It will be a distinct thing. So the equation isn't satisfied in that algebra. So that isn't the term algebra doesn't even belong to our world. So it definitely won't be free. So what we need to do is we need to combine some terms, right? And we do that by defining an equivalence relation, which is generated by phi. Okay? So we do that if we now take our equations, right? We can substitute the x, the y's, and the z's with any terms from our term algebra. And this will specify which terms have to be glued together. So now the elements of that's called the quotient algebra. So we define the equivalence relation by substituting. Well, it's generated by the equations. So whenever two terms can be proven equal under these equations, we will glue them together. So instead of individual terms, we will look at sets of terms. Okay, and these sets of terms have to be equivalent in the as specified by the equations. So for example, we take the simple signature that we have seen before. We take the monoid equations, and now we define. So that's how you write the quotient algebra, right? We divide our term algebra by the relation induced by the set of equations. So the elements of that algebra will be sets of terms. Okay, so they are like sets of equivalent terms. So let's say x contains x, y, z, and so on. So for example, we can from these equations, one element of that algebra will be the set x times 1, 1 times x, because it's this needs to be the same, right? Because of the equations. Similarly here, like it will be a large set because we can add the ones here. Well, we can add the ones here, so it will be like a much bigger set, in fact. So this will be like potential infinite sets that we can of terms that are glued together that have to be the same because of these equations. Okay, and that quotient algebra is free. Okay, so you can prove that. That's an easy exercise for home. But Yeah. So as I was saying, yeah. So the quotient algebra is free, but in the world of algebras, which satisfy the set of equations as we have said before. Okay. So now, as a hint of a proof, so now if we want to show that the quotient algebra is free, we need to build a homomorphism from this algebra to another, right? And how do we do that? How do we interpret a set of terms, right? Well, the trick is that to interpret a set of terms, we just need to interpret any one of them, because they have to the interpretation has to be the same in the target algebra because of the equations, right? So it doesn't matter which term we interpret, which term we evaluate. Okay, but let's look at this one more time. So this over here is the free monoid for that signature, right? But we also know that there's a simpler representation. There happens to be a simpler representation, and it is lists, right? So here we have sets of terms. So there should be many elements here and here as well. And this representation is isomorphic to this representation. Okay. So the free object always exists and is unique up to an isomorphism. Okay, so these are the same, right? It doesn't matter if we consider an empty list or a set containing 1 times 1, 1 times 1, 1 times 1, and so on. It doesn't matter if we consider a list containing x or all possible combination of x times 1 and parentheses, right? And so on. So here, this set of terms corresponds to this list. Okay, so in some cases we can get simpler representations in the presence of equations. Okay, so to recap a bit, so we have defined the algebraic signature, which is the language that we will be using in our considerations. Then we have said that an algebra is an interpretation of that signature, right? Then we have defined the term algebra, and we have said that the term algebra using any set for any set of variables, the term algebra using that, so the term algebra being all of the expressions that we can build using our language, using the variables, it is free, which means that for any other algebra, an interpretation of the variables extends uniquely and determines the interpretation of any term from the term algebra. Okay, so if you like in a more computer science way, you can say that if you have a program here, that's a program using the Sigma language, right? If you want to evaluate that program, it's fully determined by the way we determine the holes, the variables. Okay, that's a general construction we can apply to any type of signature. Okay, so now how do we get to monads from this? So monads are a way of modeling sequential programs. Okay, what a sequential program can do? It can do one of two things. It can return a value, right? That's the pure function, or it can compute a new value based on some previous results. That's the flat map construct, right? And people, because people didn't know how to call a thing with pure and flat map, so they decided on the name monad, which is as good as any other name. So yeah, if we want to represent programs as data, we use a monad because it's a nice representation of a sequential computation. Now monads also need to meet some sanity laws, right? So there are some sanity laws saying that if you flat map a pure value, it's the same if you don't do anything at all. Okay, so how does the free construction that we did before carry over to monads? So our signature in our case will consist of two operations, right? Pure and flat map. These are two operations using which we build our programs. Okay, so that's our signature. Our variables will be the operations in our language. So the variables will be our domain-specific language with which we want to build the programs. Okay, so we build the programs from like basic instructions being our DSL. So these are the variables, and we sequence them using pure and flat map. Okay, So now we can build terms using the operations and the variables. So now the free monad, as we defined it, right? This will be terms, so expressions built from pure flat map and our DSL, right? So for example here, right? That's an expression written using these operations. However, we have to take into consideration the monad laws. So that's an equation, right? That the free monad has to satisfy. So in fact, the free monad won't be like just pure terms. So it will be these sets of terms, right? Which are equivalent with respect to the monad laws. So now what the freeness definition really says is that if we take any other monad, right? So we are now in the world of monads, and we have the free monad, which consists of terms, right? Expressions without any special meaning, just syntax. So if we take any other monad and we provide an interpretation of the DSL of the variables, right? So this determines the interpretation of the whole program, right? The interpretation of the variables extends uniquely to an interpretation of any program built using these variables. So that's exactly what the freeness definition is telling us. Now, if we look at how free is defined in the Katz or Scala Z, so that's the Scala version, this should be quite. This corresponds quite closely to what I've been talking about. So we have two constructors. We have the pure constructor and the flat map constructor, with which we can build terms, expressions, right? So these are the signature elements, right? And using these two constructors, we can build programs, values, expressions, expressing a sequential computation. We also need a way to embed a variable or a DSL instruction, right? And that's the suspend operation over here. Okay, so these two correspond to the signature, and this corresponds to the that's a variable embedding. It needs to be wrapped, right? Because this needs to type check in Scala. So that's the free monad definition, both in Scala Z and in Katz. And so if we build a program using a free monad, what we actually do is we just build an expression without any meaning, right? It is just a value. It's really it's just a data structure, nothing very special. Only when we provide an interpretation of the variables, because of the freeness properties, this interpretation extends uniquely to an interpretation of the whole program. Now, as a final thing I would show, if we look at how free is defined in Haskell, it's a bit different. So in Haskell, I'm a Scala programmer, so I translated it into Scala so that it's more readable to me. So in Haskell, we only get two constructors, not three. So that's a bit different. So first, there's a requirement that f needs to be a functor, and second, we only have the pure and a join. So this looks a bit different. So why is it the same free monad as in the previous representation? And it turns out it is. The difference is that using that representation, each program can be represented by multiple different expressions because of the monad laws. So we can build equivalent programs using these three constructors, like two different terms, right? Will have the same interpretation because that's a monad, right? So that's like that's like the canonical construction that I've been talking about. And that's an isomorphic representation, and here each program has a unique form. So it's the same as with the free list, right? On one hand, the free monoid, so the free monoid could be either represented as a set of terms, where each element is a set of terms, or as a list. which is this, which corresponds to this representation. Okay, so in Haskell, you always have a single representation or of a program. In the Scala, you can build many equivalent representations of the same program because of the monad laws. So that's the difference, but they can be translated between each other. Okay, so to sum up what we did, so we have conducted a direct construction of free algebras for any signature, and then in a bit of a hand-wave way, it's not like a very rigorous construction, but I've shown how this corresponds to the construction of a free monad. Now free, where the name comes from, the free is free because the resulting structure can be interpreted in any way. It's free to be interpreted in any way, right? There are no constraints imposed by the free algebra, free monad on the interpretation. And keep in mind that it's a really simple thing. It's just a data structure representing your program, but it's also a general construction which we can do for any signature. Okay, and finally, before we end, just a short note about me, so that you knew who's been talking to you. Yeah, a long time ago, I've been a student of category theory. That's where I learned these things. I didn't think that they would be ever useful. It was 10 years ago. But then somehow category theory made a comeback, and well, here I am. Apart from that, I'm a Scala engineer at SoftwareMill and the co-founder of the company. We write custom software, Scala and other technologies. I have some open source projects, so take a look if you're interested. So now you know where to look for Scala engineers. You know all about free. If you want to know more about this thing, there's a very nice book which I used when I was learning these things. Andrzej Terlecki is my professor at the University of Warsaw. So you can buy the book on Amazon. So in the book there's an introduction to algebras, universal algebras, category theory, and then on top of category theory there's a whole section on formal specifications. So the book contains a lot of examples, and so if you're interested, I recommend that. And with that, I guess I'm done. So thank you very much. And